Welcome to the University of Waterloo's Mechanical Engineering Information. If you're interested in designing machines, solving real-world problems, or working in industries like energy, aerospace, and manufacturing, this is a great place to start. My name is Abby, and I'm the undergraduate recruitment specialist for the Faculty of Engineering at Waterloo. In this session, I'll give you a quick overview of our mechanical engineering program, including what you'll study, the kinds of hands-on experiences you can expect, the co-op opportunities available, and where this degree can take you after graduation. First of all, what exactly is mechanical engineering? Mechanical engineering is one of the broadest and most versatile fields in engineering. If you're interested in designing machines, improving energy systems, working in automotive, aerospace, or health tech, this program opens the door to all of that and more. Mechanical engineering combines physics, math, computing, and creativity to build solutions in every major industry, like energy, aerospace, healthcare, manufacturing, and robotics. A simple way to think about it is we design anything that moves and more. Waterloo's Mechanical and Mechatronics Engineering Department is the largest of its kind in Canada, with 63 full-time professors and expertise across a wide range of exciting fields. For example, we have leading research in additive manufacturing, autonomous vehicles, green energy, and assistive technologies like exoskeletons. Our RoboHub is a unique multi-robot facility, one of the only ones in the world to bring together ground, aerial, humanoid, and magnetic levitation platforms under one roof. From advanced robotics to micro-electromechanical machines, the work happening here is pushing the boundaries of what's possible. The Mechanical and Mechatronics Engineering Department is committed to fostering a positive and supportive environment. One unique feature of the program is its cohort system, where students take courses with the same group of approximately 90 to 120 classmates throughout their entire degree. Cohorts typically remain in the same classroom for lectures during the day, helping to build strong connections and a close-knit academic community. Hands-on learning is embedded throughout the curriculum. In first year, students participate in the Engineering Ideas Clinic, where they begin developing practical engineering skills through structured design challenges, prototyping exercises, and experimentation. As students progress throughout the program, they gain experience with machining, measurement tools, control systems, and lab-based investigations across areas like thermodynamics, fluid mechanics, materials, and manufacturing processes. This hands-on philosophy extends into the upper years of the program, including ME 380, a third-year mechanical engineering course focused on design and competition. In this course, students apply their technical knowledge to solve open-ended design challenges, often in the form of a friendly competition. Teams might be tasked with designing a structure that can hold the most weight using limited materials, or building a device that can race across an obstacle course. The projects require not just creativity and engineering skill, but also teamwork, testing, and iteration, mirroring the kind of challenges that students will face in the workplace. The images on this slide show a few past examples, structures being tested to failure, robotic systems in action, and team-based design showcases. It's a great example of how theory and hands-on learning come together in mechanical engineering at Waterloo. In fourth year, all engineering students participate in a capstone design project. Working in teams, students identify a real-world problem and design a solution to address that need, applying everything they've learned throughout their degree. This work culminates in the design symposia, where students publicly present and demonstrate their projects to classmates, faculty, and industry partners. Projects span a wide range of industries and challenges. Past examples include robotic hockey stick testers, drone applications for package delivery, automated greenhouse systems, and assistive technologies for individuals with vision impairments. These projects are an opportunity to showcase not just technical and design skills, but also communication, creativity, and teamwork. For many students, it's one of the most rewarding and memorable experiences of the program. In first year, mechanical engineering students at Waterloo build a strong foundation across key areas of math, science, and engineering fundamentals. This includes calculus, linear algebra, and mechanics to support problem solving and analysis. Students are also introduced to material science, basic electrical engineering, and chemistry for engineers, all tailored to mechanical applications. Courses in engineering practice and communication help students develop teamwork, ethics, and design skills early on, and a complementary studies elective allows students to explore a non-technical subject of interest. Altogether, the first two curriculum sets the stage for more specialized and hands-on learning in upper years. Let's walk through the four major subject areas that students explore in mechanical engineering. The first is the foundation of mechanical engineering, mechanics and materials. Students begin by learning statics and dynamics, how forces act on objects, how structures remain stable, and how motion occurs. They use tools like free body diagrams and equilibrium equations to analyze forces and apply Newton's laws, energy methods, and momentum principles to predict motion and mechanical behavior. They then build on this with mechanics of materials, studying how materials respond to different types of stress like tension, shear, and torsion. This includes analyzing beams, columns, and shafts, and understanding failure mechanisms such as fracture, fatigue, and buckling. This subject area also introduces students to machine design, how to ensure mechanical components are strong enough and safe enough for real-world applications. Understanding mechanics and materials is critical for designing everything from bridges and vehicles to medical devices and robotic arms. The second major subject area in mechanical engineering is thermofluids and energy systems. This area brings together thermodynamics, fluid mechanics, and heat transfer, three core disciplines that help engineers understand how energy moves and transforms in mechanical systems. Students start with thermodynamics, where they learn the laws of energy conservation and efficiency. These principles are the basis for designing engines, turbines, refrigerators, and power plants. Key concepts include thermodynamic cycles like the Otto, diesel, and Rankine cycles, used in everything from car engines to jet turbines. Next is fluid mechanics, which explores how liquids and gases behave in motion. Students study concepts like pressure, flow rate, turbulence, and aerodynamic drag. These principles are critical in applications such as aircraft design, water systems, pumps, and compressors. Heat transfer is the third component, focused on how energy moves through conduction, convection, and radiation. This is important for designing things like radiators, cooling systems, electronics, and building insulation. Students also explore energy systems and sustainability, looking at how to design more efficient and environmentally responsible power sources. This includes work with solar, wind, geothermal, and hydrogen fuel cells, along with energy storage technologies. Finally, there's a focus on HVAC systems, used for climate control in buildings, vehicles, and industrial spaces. Students learn how to optimize these systems for energy efficiency and comfort using smart sensors and automation. Altogether, thermofluids and energy systems form the backbone of modern energy technologies, helping mechanical engineers tackle big challenges like climate change, clean energy, and sustainable infrastructure. The third major subject area in mechanical engineering is manufacturing and production, which focuses on how products are designed, fabricated, and optimized for large-scale production. Students begin by learning about manufacturing processes, including traditional methods like machining, casting, molding, and joining. These are used in industries like automotive and aerospace to shape and assemble components. The course material also covers modern techniques like additive manufacturing or 3D printing and micro-nano manufacturing for electronics and biomedical devices. The program also introduces students to automation and robotics in manufacturing. This includes CNC machining, industrial robotics for assembly and welding, and smart factory technologies like digital twins and AI systems that monitor production in real time. Another key area is quality control and manufacturing optimization. Students explore concepts like statistical process control, lean manufacturing, and Six Sigma, all aimed at improving consistency, efficiency, and reducing waste in production. Finally, there's a growing emphasis on sustainable manufacturing. This includes selecting eco-friendly materials, designing energy-efficient processes, and evaluating environmental impact through life cycle assessments. Understanding these systems is essential for turning engineering designs into real-world products efficiently, affordably, and sustainably across industries from healthcare to consumer tech to transportation. The final core subject area is control and mechatronics. This field combines mechanical, electrical, and software engineering to create smart, automated systems, like robotic arms, self-driving cars, and intelligent manufacturing equipment. Students start by learning about control systems, which allow machines to monitor their performance and make real-time adjustments. This includes everything from cruise control in cars to temperature regulation in industrial furnaces. They study control strategies like open loop and feedback control, including techniques like PID control, which helps stabilize systems like drones or robotic platforms. Next, students explore how machines interact with the physical world through sensors, actuators, and embedded systems. Sensors collect data like position, speed, or temperature, while actuators perform motion or force-based actions. Embedded controls process this information in real time to keep systems running smoothly. The program also covers robotics and autonomous systems, where students learn how to build and program intelligent machines, from robotic surgical tools to warehouse robots and autonomous vehicles. Topics include motion planning, computer vision, and even swarm robotics. In smart manufacturing, students see how control and mechatronic drive Industry 4.0, using automation, connected sensors, and digital models to make factories more efficient and responsive. Finally, there's a focus on human-machine interaction and assistive technology, including exoskeletons for mobility, haptic feedback systems for simulation and gaming, and brain-machine interfaces used in advanced prosthetics. This subject area is essential for engineers working in automation, robotics, and any technology that blends physical systems with intelligence and adaptability. In the upper years of mechanical engineering, students explore advanced topics that integrate mechanics, materials, control systems, thermodynamics, and manufacturing. These areas reflect real-world innovation and emerging technologies. Examples include prosthetics and exoskeletons for mobility and rehabilitation, soft and humanoid robotics for human interaction, aerodynamics for aerospace and automotive performance, extreme temperature systems, including cryogenics and fusion, smart and self-healing materials for safety and longevity, hyperloop and high-speed rail design, renewable energy systems like solar thermal and wind optimization, and vehicle dynamics and control for electric and autonomous vehicles. These topics allow students to apply their skills to cutting-edge problems in health, transportation, energy, and beyond. In addition to your core degree requirements, you may choose to add a specialization or an option to focus on a specific area of interest. Specializations are program specific and typically involve completing 4 to 6 designated courses. In mechanical engineering, one specialization is available, welding and joining, which can be added in the upper years of the program. Options are available across all engineering programs and usually require 5 to 8 courses. Popular choices among mechanical engineering students include biomechanics, artificial intelligence, and mechatronics, though there are a total of 13 options to choose from. These additions allow students to tailor their degree towards specific industries or emerging technologies of interest. At Waterloo, mechanical engineering students gain valuable real-world experience through North America's largest co-op program. Students complete 5 paid work terms as part of their degree, applying classroom knowledge in professional environments and building meaningful industry connections. Co-op positions span a wide range of industries and roles, from product design and manufacturing to robotics, automotive systems, aerospace, and energy. This variety allows students to explore different career paths and develop both technical and professional skills. And it's a system that works. 96% of our co-op graduates find employment related to their skills within 6 months of graduation, compared to just 83% for Ontario University grads overall. These experiences often lead to full-time job offers and give students a strong head start in launching their careers. There are 2 possible sequences in mechanical engineering, both of which alternate between academic terms and co-op work terms. The program follows a 5-year format with 6 co-op work terms integrated into the academic schedule. Students switch between study terms and co-op terms throughout their degree. This format allows students to apply what they learn in real-world settings while earning valuable industry experience. This structure is what makes Waterloo's co-op program unique. It provides a balance between academic learning and practical industry experience. Whether students are in Stream 4 or Stream 8, both pathways lead to a strong foundation for future careers. A degree in mechanical engineering opens doors to a wide range of career opportunities across many sectors. Because of its broad foundation in mechanics, materials, energy systems, and automation, mechanical engineering is one of the most versatile engineering disciplines. Graduates find roles in manufacturing, energy and sustainability, transportation and mobility, aerospace, healthcare, and biomedical engineering, robotics, and advanced automation. Some work in design and product development, while others move into project management, consulting, or technical sales. The flexibility of this degree allows graduates to follow a path that aligns both with their interests and with evolving industry needs. Many graduates also choose to pursue further education, such as a Master of Engineering, a Master of Applied Science, or a PhD. Whether entering the workforce directly or continuing with graduate studies, mechanical engineering graduates leave the program well prepared to make meaningful contributions across a wide range of fields. That brings us to the end of this session. Thanks so much for watching. If you have more questions, don't worry. There are a few great ways that you can follow up and get more information. If you'd like to hear directly from our current students, check out our Ask a Warrior chat platform. You can connect with real Waterloo engineering students to ask about academics, co-op, residence, student life, whatever's on your mind. For admissions-related questions, like requirements, timelines, or the application process, please feel free to reach out to our team at enginfo@uwaterloo.ca. And if you're thinking about visiting campus or joining one of our events, head over to our tours and events page to see what's coming up, whether that's an in-person or virtual. Thanks again for tuning in, and we hope to see you at Waterloo Engineering soon.